Welcome to the second lecture for Geology 102. We'll be talking about warming the Earth's atmosphere, specifically early topics related to energy, radiation, convection, and other ways of warming the Earth and its atmosphere. Well, I did mention energy, and so the question is, why do I care about energy? Isn't this a course about weather? It is. Just stay with me for a few more minutes. We have to learn a little bit about energy, and to learn about energy we should probably look at the sources for energy. Ask these questions. How does the energy warm our Earth? And does the energy play any role in our weather? To answer these questions we need to define what we mean by energy. Well, energy in its simplest form, it's just the ability to do work on something. For example, if you're into lifting weights, when you do work on the weights, let's say you're doing a bench press, and when you're lifting the weights off of your chest, you're doing work. And to do work, you need energy. Your body, specifically your muscles, provide energy to be able to do work. In other words, be able to lift those weights off of your chest. Can you come up with some other examples of work? An example that I like to use is, and I do this in class every semester, I'll take the textbook, your Essentials of Meteorology textbook, and I'll ask a student to lift or to move his or her foot out into the aisle. And the reason I do this is I'm trying to show how the book can do work on the student's foot. If I were to drop the book, it will do work on the foot. Painful work, but it will require energy, the energy that the book provides. And in fact, as I hold the book over the student's foot, it's a certain distance away from the foot, the book has a mass, and gravity is actually taking effect on the book. We define this as potential energy. In other words, the book has potential to do work, in other words, to provide energy to the student's foot. So the book has a mass, gravity plays a factor, and I hold the book a certain height over the student's foot. Now I haven't dropped the book yet. All I've done is just holding it over the student's foot. We say that the book has potential energy. In other words, the ability to do work on the foot if I drop it on the foot. In terms of meteorology, we talk about air parcels, and we'll get into that later in the semester. But pieces of air that are above the ground, they have a mass, they're affected by gravity, and they're a certain height above the Earth's surface. Anything that has a mass that's influenced by gravity and is a certain height above a reference point has potential energy. The other part of energy that we'll look at here, and you're probably more familiar with this, kinetic energy. It's the energy associated with movement. As soon as I take that book and I drop it, the book will begin to move. It has a mass, and the book is moving at a certain velocity. And we square that velocity, multiply it by mass, multiply it by 1/2, and we come up with kinetic energy. So internal energy, that's a term you'll want to store away. Internal energy is made up of potential energy and kinetic energy. All objects have some form of potential energy and kinetic energy. In weather, the blowing of wind or the movement of water in a stream is associated with kinetic energy. So initially, the book, which is being held above the student's foot, before it's dropped, it has potential energy. As I release the book, it begins to drop. Its potential energy begins to decrease as the height decreases. Its velocity begins to increase, so its kinetic energy begins to increase. So we're converting energy. We're taking this internal energy, we're converting it from potential energy to kinetic energy. Eventually, the book hits the student's foot and imparts work. To do that, it needs energy. Now that we've defined energy, the ability to do work, let's talk about some of the characteristics that energy has. It can take on many forms. It can be in the form of heat, chemical, or mechanical type of energy. The type of work that you were doing on the weights when you were doing bench pressing, your arms are providing the energy, mechanical energy in this particular case, to move the weights off of your chest. If we talk about heat energy, which we will a little bit later in this particular chapter, that's a very important concept. Chemical energy also. One thing that's nice about energy, or a characteristic, is that we can change it from one form to another. In other words, we can take water vapor, and water vapor is water in the gaseous form, and we can turn it into liquid, or we can take liquid water, turn it into water vapor, or if you take an ice tray, fill it with liquid water, put it in the freezer, you'll take that water and convert it from liquid to solid. So energy can change many forms. Think about for a second when you strike a match. The match itself has chemicals on it. You strike it and you go from chemical energy to producing heat energy by striking a match is an example of this. Another characteristic of energy is that energy cannot be created or destroyed. You've heard this before. Specifically, it's called the first law of thermodynamics. And don't worry about this equation here. Just understand the terms. I won't ask you to memorize it. But the first law of thermodynamics, in other words, the energy remains constant, you can't create it or destroy it, is that it's made up of heat energy, it's made up of internal energy, and on the last slide we talked about internal energy being made up of potential energy and kinetic energy, and work. So you've got Q, U, and W in this equation. And what this says is that heat energy is dependent upon the amount of internal energy plus the work done on an object or what the object does work on. Again, you will not be held responsible for the first law of thermodynamics, but each of these individual components you will be familiar with as we work through this chapter. Okay, we've defined energy, we've talked about the characteristics of energy. Let's look at the relationship that energy has with temperature and air density. Now, what you're looking at here is an air parcel. And this is an air parcel. And within the air parcel, as we learned from Chapter 1, a piece of air, and that's all an air parcel is, it's just a piece of air that we've grabbed out of the air. It's made up of different atmospheric constituents, different gases, such as nitrogen, which makes up 79% of this air parcel, oxygen about 20%, and other trace gases that you find in here. So we have this air parcel made up of gases, and if we begin to warm this air parcel, if we begin to warm it up, okay, what do you notice about the warm air parcel compared to the cold air parcel? Well, first of all, you notice it's larger. So you notice that the warm air parcel begins to expand. Okay, so there's some relationship between warming and expansion of air. The different molecules that we have in here, hydrogen, oxygen, and other trace gases, what can you say about the speed of these air molecules? Now think about the speed in terms of the length of the tail of this particular molecule. Now over here, the length of the tail of these molecules are shorter than when they're warmed up. So in other words, air molecules that are warm not only expand, or the air parcel not only expands, but the molecules inside the air parcel begin to move much more quickly. So there seems to be some relationship between temperature and the speed of molecules. Now we'll define that a little bit later. Now, on this particular graph here, you see you have on the y-axis you have altitude. This is how high above the surface of the Earth, and this 0 kilometers is the surface of the Earth. And if I go up about 200 kilometers, that is about 120 miles. So it's about 0.6 is the conversion factor. If we go up to 400 kilometers, that's roughly 240 miles above the Earth's surface. Now, what I'm going to ask you to do is to look at how air density and how air pressure changes as we go up in height. Now, recall in Chapter 1 we defined air pressure. Air pressure is the force per unit area. In other words, the force that air molecules exert over a particular area. And air density we also talked about. It's the spacing between the molecules. If I were to go back here for a second to this warm air and ask you to tell me, is the density increasing or decreasing compared to when the air parcel was cold? So looking at the warm air parcel, has the density increased or decreased? Well, if we look at the air molecule, the cold air molecule, the spacing between the air molecules is very small. So it's very dense. These molecules are packed in. So we've got another relationship here between temperature and air density. It appears that warm air is what? It's less dense than cold air. So let's look at air density and see how it changes from the surface of the Earth as we go up into the atmosphere, and we see that density begins to decrease very rapidly. You see the curve here. And density as we go up to about 200 kilometers, still decreasing, but not as rapidly. And if you look here at this column of air, again, this is very familiar from the first lecture, we have a column of air starting at the surface going all the way up to about 300 miles above the Earth's surface. And notice that all the air molecules are tightly packed together here. Most of the air molecules are very close to the surface, and that's because of the effects of gravity. Gravity tends to pull the air molecules down. And so the density near the Earth's surface is high. See, if we look at density and at 0 kilometers, we see that the density is very high. And you can actually see this here. The air molecules are all packed together. But what do you notice about the density of air molecules as we go up to about 200 to 250 kilometers? Now the spacing between each of these molecules is larger, so density is decreasing with height. And that's a function of gravity. Now what about air pressure? Same thing. Air pressure decreases rapidly as we go up into the atmosphere. And remember from Chapter 1 that we define density as the force per unit area. Let me go ahead and clear this off just for a moment. It's getting a little messy here. Now, if I were to ask you to define how much the pressure is at the surface, what we could do is look at the force per unit area that each of these air molecules exert in this entire column of air. So we're looking at the force per unit area of all of these air molecules above the Earth's surface. Well, when we look at that, the average pressure is about 1,013 millibars. Now, if I were to let's say draw an arbitrary line here, and I were to ask you to tell me what the pressure is from about 250 kilometers on up to 500. In other words, what is the pressure at 250 kilometers? If we look at the air molecules above it, there's a lot less air molecules above this particular level. The first level we were looking at was the surface. This particular level at about 250 kilometers, we look at the concentration of air molecules above this level, and we see that it's much less. So the pressure would be much less here. And so we see that both air pressure and density begins to decrease rapidly. Well, let's look at a definition here. Temperature. It's basically a measure of the average speed of atoms and molecules. Recall we go back here to this particular picture, and we see that the average speed of these air molecules inside this parcel of air is moving much more quickly, having many more collisions than the colder air parcel, where the air parcels are moving much more slowly. And so, temperature is based upon the average speed of atoms and molecules. So in other words, if you have less energetic molecular movement, in other words, the molecules aren't moving around as rapidly, that means colder, more dense air. If you have very energetic molecules, in other words, there's a lot of energy being provided to these molecules, then they will be more energetic, more collisions, faster molecular speed, so they will be warmer, less dense air. And you can go right back to this particular slide and see that. Notice that the warm air here is less dense. In other words, there's more spacing between the individual molecules. The molecules are moving much more quickly, and so warm air is less dense and faster molecular speeds compared to cold air. We will look at temperature scales here. For this particular course, we're going to mainly use Celsius, and you'll learn how to read Celsius or to interpret temperatures in Celsius. But there are three temperature conversions. We can look at temperatures in degrees Kelvin, degrees Fahrenheit, and degrees Celsius. And I may give you an in-class exercise just so you can do some of these conversions. But notice here that boiling, which is 212 degrees Fahrenheit, is equivalent to 100 degrees Celsius or 373 degrees Kelvin. Freezing in Fahrenheit we know is 32, but in Celsius it's 0, and in Kelvin 273. What I would recommend that you do is, if you want to come up with degrees Celsius and freezing, plug in 32 for Fahrenheit, so you'll have 5/9 times 0 gives you a temperature of 0. If you were to plug in 212 here, you would do 212 minus 32, which would give you 180 times 5 is 900 divided by 9 would give you 100. So you'd see that Celsius is in 100. So you should really know how to go back and forth between Celsius and Fahrenheit. Kelvin, as you can see, is really easy. Just take the degree Celsius and add 273 to it to arrive at the Kelvin temperature. So temperature indicates how hot and cold, but it doesn't tell us anything about the amount of internal energy that an object possesses. Remember, we talked about potential energy being made up of mass times gravity times height. Do you see anything in there with temperature? I don't. Kinetic energy, 1/2 mv squared, mass times velocity squared. Do you see a temperature in there? I don't. So temperature gives us an indication of how hot or cold something is, but doesn't tell us directly about the amount of internal energy that something possesses. Now, let me ask you this. let's say we have a cup of hot tea and we pour it on top of the Mississippi River. Which one is warmer? The hot tea or the Mississippi River? Think about this. Well, on an average day, the hot tea, especially if it's boiling, is going to be a lot warmer than the Mississippi River. But let me ask you this, which one has more energy? Does the hot tea have more energy than the Mississippi River? Or does the Mississippi River have more energy than the hot tea? Are they the same? Well, let's look at this. If we were to define the potential energy of that cup of tea, it's equal to the mass times gravity times height. The mass of that hot tea, that little cup of hot tea, is going to be less than the mass of the Mississippi River. So right there tells you that the Mississippi River has more potential energy. Well, what about kinetic energy? We know that kinetic energy is 1/2 times mass times velocity squared. Which is moving faster, the hot tea or the Mississippi River? Well, the Mississippi River is moving much more quickly than the hot tea. And the mass of the Mississippi River is quite a bit more. So the kinetic energy of the Mississippi River will be greater. So the energy of the Mississippi River is greater than the energy of the hot tea, but the tea is warmer than the Mississippi River. So you see, while temperature indicates the degree of warming or cooling, it doesn't tell us anything directly about the internal energy. Time. Let's say, for instance, it's -10 outside, and you come inside and you want to grab a hot cup of coffee or cocoa, and your cold hands begin to touch the hot mug, and your hands begin to feel better. That's because some of the energy in the form of heat is being transferred from that warmer mug of coffee or cocoa to your hand. Once the energy is transferred, it's stored as internal energy. Now, recall again what we said about internal energy. It's made up of potential energy plus kinetic energy. And specifically looking at this kinetic energy, the molecules of that cup, that warm cup, is moving more than the molecules in your hand, which is cooler. And so, some of those warm molecules from that cup begin to transfer directly toward your hand. And when some of those more excited molecules from the warm coffee mug begin to touch your hand, it begins to excite the molecules on your hand. And so the molecules begin to speed up, and the temperature of your hand begins to increase. Because recall, we talked about temperature being a measure of the speed of movement of those molecules. Now, there are 3 methods of transferring heat energy. Conduction, which is what I just talked about with picking up the warm coffee mug. It's direct contact. We'll talk a little bit more about that here in a few minutes. Convection, transfer of energy vertically in the atmosphere. And then radiation, which is really where we're going to spend most of our time in this chapter, talking about radiation, energy being transferred through waves, electromagnetic waves. We'll talk about that in a few minutes. But before we get into the specifics of these methods of transferring heat energy, let's look at two physical concepts of heat. There's something called specific heat and something called latent heat. Now you may or may not have heard of these particular terms, and while you may not recognize them, you recognize the effects from them, and we'll talk about that here. You've seen this before or heard this: a watched pot never boils. You go home, you put a pot of water on the stove, and you look at it, and you've got the heat cranked up, and that pot seems to never boil, or the water in the pot never seems to boil. Let's look at the results of our experiment that we did in the first day of class. Remember that? We had some dry sand and some warm sand. Some dry sand and moist sand. And we saw that temperatures changed differently for the wet sand compared to the dry sand. What's going on here? Why did that happen? Why did the dry sand heat up and cool down much more quickly than the moist sand? Well, I ask you, what did you observe with the wet soil in terms of temperature change? You noticed it did not warm up or cool off as quickly as the dry sand. So why? Well, we need a few more items before we can figure this out. And in fact, we'll need to define another word: heat capacity. And heat capacity is basically a fraction, just like what we had in grade school. It's the amount of heat energy absorbed and its change in temperature. So if we were to write this out as a fraction, we would say that heat capacity is equal to heat energy absorbed how much heat is absorbed, divided by the change, or I'll mark this as delta, delta meaning change, the change in temperature. Now, you remember with fractions, if the numerator becomes larger than what you're looking at, in this particular case, the heat capacity. So, if we increase the amount of energy absorbed of an object, whatever that object may be, your hand, a piece of steel, anything, its heat capacity begins to increase. If, however, the denominator is larger than the numerator, then heat capacity begins to decrease. So if we have a change in temperature, a very rapid change in temperature, higher change in temperature compared to the heat energy absorbed, then we would say an object has a very low heat capacity. Well, now in meteorology and in physics, we don't look at heat capacity. We look at something called specific heat. And all specific heat is just another fraction. It is the ratio of heat capacity divided by a unit mass. Let's just say we've got 1 gram. So if you took a gram of sand and you look at the heat capacity of 1 gram of sand, or 1 gram of water, or 1 gram of mud, or 1 gram of ice, clay, dry air, you will get something called its specific heat value. Let's go back here a second. Again, heat capacity is the amount of heat energy absorbed by an object, whether that object is a piece of sand, piece of water, piece of mud, and how much its temperature changes divided by 1 gram of that particular object. So we say that the specific heat of water its reference value is 1. Now, the specific heat of water is a lot larger, in other words, about 5 times larger than quartz sand. Okay, so specific heat for water is higher than the specific heat of sand. What does that mean, and why do I care? And in fact, the specific heat for water is 5 times larger than the specific heat of sand. Well, again, let's look at the formula for specific heat. It's heat capacity divided by a gram or a kilogram of an object. So in other words, we're saying that water has a higher heat capacity than sand. Right? We look at heat capacity, we're saying water has a larger capacity for heat energy than sand. If we go back, again, looking at the formula for heat capacity, it's the amount of energy absorbed by the change in temperature. So what we're saying is that water can absorb a lot more energy before it changes by 1 degree Celsius compared to sand. So in other words, think about it like this. If you go to the beach on a hot day, I don't know if many of you have been to a beach. We're sitting here in the Midwest, but I'm sure some of you have been out there to the coast. And if you've ever walked barefoot across the hot sand, you probably sprinted to get into the water because the water was cooler on your feet than the actual sand. Now the sand and the water are both absorbing energy from the sun, but the temperature of the sand increases much more quickly than the temperature of the water. In other words, the sand doesn't have as much capacity for heat energy as compared to water. In other words, it takes a lot more energy, in this particular case from the sun, to warm or to increase the temperature of water by 1 degree Celsius compared to sand, where you need 5 times. The best way to look at this is, let's say, for instance, here's the water. Okay, so this, actually, we can use this screen back here, this backdrop. You see the water back here, and let's say we had a little island of sand. If we wanted to show the change in temperature of the water to be the same as the change in temperature of the sand, we would need 5 times the energy going into the water than the sand. Another way of looking at this, if the sun is our energy source, we would need 5 suns putting out energy into the water compared to 1 sun putting energy into the sand to both produce an increase in temperature of 1 degree Celsius. Okay, so you understand specific heat. Why do we even care? Well, you'll see here in just a moment. Now, again, we look at specific heat. In other words, it cannot hold as much heat energy without changing temperature compared to water. Why do we care? And what does this have to do with the experiment of our moist soil versus dry soil? Well, before we solve that riddle, let's talk about latent heat. Just to give you a heads up, this is a very important aspect of this particular course. And we'll define latent heat as heat energy required to change the phase of a substance. In other words, in our example, we're going to look at water. So it's the amount of heat energy. Let's say, for instance, we look at this piece of ice here. So we've got ice here. To change this ice from ice to liquid, this ice is going to have to absorb some energy. So we've got to figure out how much energy does it take to change this from solid to liquid. And in fact, we can take energy and add to this liquid water and eventually create water vapor, or water in the gaseous state. So if we go from ice to liquid to vapor, the object actually has to have heat energy transferred to it. Now what happens when we transfer energy to an object? What happens to the molecular speed? Well, if the molecules of that ice is receiving energy, the molecules of the ice will begin to get excited and will begin to move much more rapidly. Its temperature will increase. What happens to water, liquid water, if we provide more energy to the liquid water? Well, its molecules, the molecules of the liquid water, begins to get excited and begins to move away from the liquid water. And in fact, it will produce a process called evaporation. Now that's going from solid to liquid to water vapor. We'll talk about this process going the other way, vapor to liquid to ice, in a few minutes. So, here's a question for you. You've got a beaker here, and inside the beaker is water. And then above the level of the water, you have air. And in fact, what you're seeing here are water molecules, 2 atoms of oxygen, H2O, 2 atoms of hydrogen and an atom of oxygen make up water. Some of these air molecules, or some of these molecules of water, are leaving the surface of the water. Some of these air molecules are going from the air to liquid. And so what would happen to some of these air molecules, or to some of these water molecules, if I were to begin to excite these water molecules that are in the liquid? Well, they would become more excited. They would begin, some would move this way, others would move up, going from water to vapor. And if I have more and more of these water molecules going from water to vapor, what is occurring? Well, the level of the water will begin to decrease. And what happens to the temperature of the water of the molecules left behind? In other words, some of the more excited molecules begin to leave. Some of the molecules that move much more quickly begin to leave. And now the molecules that you have left here are the slower moving molecules. Do you remember what we said about the relationship between the speed of molecules and temperature? We define temperature as the average speed of molecules. And so the faster the molecules move, the higher the temperature, and conversely, the slower the molecules move, the cooler the temperature. So in other words, we have the slow molecules left in the water state, and so we have cooler water. In other words, we're evaporating this water from liquid to gas. And so evaporation, which is what is occurring here, we're evaporating water. Evaporation is a cooling process. So something to note. Evaporation, cooling process. Okay, this is something we experience every day. At least we hope so. Hopefully you all take showers every day. Let's say this gentleman here, as soon as this gentleman steps out of the shower and steps into drier air. And in fact, this is what is happening these days as we sit here in January of 2008. The air is pretty dry these days. In fact, I had to get a humidifier recently to increase the moisture content of the air in the house. But what happens when you step out of the shower into drier air? Well, you begin to feel cold, right? You reach for that towel quickly because you're getting cold. Well, the second question is, why does the temperature of our skin change this way? Why do we get colder? Why does our temperature decrease? Well, what is the relationship between temperature and average speed of molecules? Well, if the speed of molecules begins to slow down, what does the temperature do? Does it increase or does it decrease? It decreases. If the average speed of the molecules were to increase, then the temperature would increase. So let me ask you this. The molecules on your skin, if you're getting cold, what can you say about the average speed of molecules on your skin? Well, they're pretty slow. So what is happening? Well, we can go back to this particular slide here that we were talking about. Let me erase all the ink on here. We said that the more energetic water molecules, the ones that were moving fast or faster, begin to escape. And so they go from liquid to water vapor. In other words, they begin to evaporate. And the molecules that are left in the liquid state here, they're less energetic, so their temperature is lower. Temperature is lower, less energetic. We said evaporation is a cooling process. It's the same thing that's happening here when you step out of the shower. As you step out of the shower, the more energetic air molecules begin to leave your skin. And the molecules that are left on your skin are slower moving molecules. We have evaporation, water going from liquid, the liquid water beads on your skin, to gas as it begins to evaporate. So let's talk about this graphical discussion of latent heat. Now if I go back a few slides, we have a definition for latent heat. It's the heat energy required to change the phase of a substance. In other words, to change from solid to gas, gas to liquid, or vice versa. Now, again, we're going to look at going from ice to liquid to eventually water vapor. Let's specifically look at this liquid droplet, because I just gave you an example of someone stepping out of a shower and having liquid water drops on their skin. Now, to evaporate the liquid water, we have to have energetic air molecules. Your skin provides some of the energy for those water molecules, but also the surrounding air provides. There's a transfer of energy, in other words, from the air to the liquid water beads on your skin. And let's just say the energy coming from the surrounding air, the heat energy going from the surrounding air to the liquid water drop begins to excite the liquid water drop, and it will change phase. It will go from liquid. It will evaporate. It will go from liquid into water vapor. Now, we talked about the first law of thermodynamics. We said that energy cannot be created or destroyed. It just changes form. Well, the energy that's being absorbed by this water molecule, by the surrounding atmosphere, is being stored in the water vapor. And we can't destroy that energy. That energy coming from the environment is stored as something called latent heat. And what we mean by latent, it's heat that's hidden. There's not a temperature change here as we go from liquid to water vapor. It's just being used to take liquid water and evaporate it into water vapor. So that energy taken from the environment, from the surrounding air, is still stored in there. Now let's say, for instance, we take this water vapor and we go the other way. We go from water vapor to liquid. Now this latent heat, or the stored energy, is now released to the environment. And it's released as something called sensible heat. We talked about two types of heat energy: latent heat energy and sensible heat. When we mean sensible, we mean this is the type of heat that we can feel. So in clouds, where you have water vapor, let's say you have this cloud, and inside the cloud is water vapor. Once we go from water vapor to liquid, the latent heat is released as sensible heat, warming that we can feel. So why do we care? Well, I'll come back to that in a moment. So the question is, have you solved the mystery of the change in soil temperature? Why is it the moist soil could not heat up as quickly as the dry soil? Have you solved that mystery based upon what we've talked about? So now the question comes in, why do we care about latent heat? It's an important source of atmospheric energy. Latent heat release, when you're going from water vapor back to liquid, the sensible heating that you feel is very important to the development of clouds. And to produce severe thunderstorms, you have to have clouds. And within those clouds, you have to have things going on, which we'll talk about a little bit later. But latent heat, specifically latent heat release, is very important for providing energy to the atmosphere. Okay, now that we have some of the terminology and some of the concepts straight in our head, let's look at the three methods of transferring heat energy in the atmosphere. We've mentioned them briefly before: conduction, convection, and radiation. And by the way, we'll be spending most of our time in this chapter with radiation. But we need to learn a little bit about conduction and convection. Conduction is simply the transfer of heat energy, direct contact from molecule to molecule. In this particular example, this hand here is holding a pin, a metal pin, and the molecules from the flame, which are moving very excitedly, contact the molecules in this pin, and begin to excite the molecules in the pen, and the excited molecules begin to reach the hand and begin to increase the speed of the molecules in the hand, which increases the temperature of the hand. So that's why if you touch a metal pot, you get your hands burned. So let's look at some characteristics of conduction. It occurs from warmer to colder. So the energy is transferred from warmer to colder regions. The more the temperature, or the greater the temperature difference, the faster the heat transfer, or the rate of heat transfer. That's similar to that warm coffee mug that I was talking about earlier in this module. So if your coffee mug is very warm, your hand's very cold, there's a large difference in temperature. The faster that heat will be transferred from that warm mug to your cold hand. And we say that when the transfer from molecule to molecule is easy, we say that the substance is a good conductor of heat. And in fact, when we talk about conduction, the question that we ask, is this an effective way of transferring heat in the atmosphere? Well, let's look at this particular chart here briefly. The heat conductivity, in other words, the ability for heat to be transferred by conduction, in other words, direct contact, in terms of looking at it, still air versus silver. Silver has a very high heat conductivity. In other words, it's very efficient of transferring heat by direct contact, whereas the air is a very low value. It's not even 1. It's 0.023 watts per meter per degree Celsius. So still air is not a very good way of transferring heat energy in the atmosphere. So let's look at convection. And you'll notice I put lava lamp here because one of my students, I believe it was in the summer 2007 class, described convection as a lava lamp. And what do we mean by that? Well, we talk about the Earth's surface here being heated by the sun unevenly. In other words, the surface is hotter or warmer here than the surface surrounding it. And so this warm air, we talked about warm air being less dense, and if it's less dense, it will want to rise. And so we have hot air moving up, and the cooler air replacing the warm air at the surface. And eventually you'll get this big bubble of hot air, and then the surface will be warmed again, and this bubble of warm, less dense air begins to rise. It looks like a lava lamp. So convection is the transfer of heat energy by the movement of a fluid, in this particular case, warm air. Here's an example of the sun's energy coming in, warming the surface unevenly. The warm air begins to rise, and as we'll learn a little bit later, the air cools and it reaches saturation. Again, we haven't talked about that. But as the air begins to reach saturation, we begin to go from water vapor to liquid. Recall, when we go from water vapor to liquid, the hidden heat, which is latent heat, is released as sensible heating, releases energy in the atmosphere. So convection is a way of transferring energy throughout the atmosphere. But the big player here, in terms of heat transfer in the atmosphere, is what we call radiation. Radiation is defined as energy that comes from the sun. It travels in electrical and magnetic waves. And the energy is released when the waves are absorbed by an object. So for instance, let's take a look at your skin. You've noticed on a warm day, you're walking around and you're out in the sun, and so your skin begins to absorb energy from the sun. Radiant energy, energy in the form of electrical magnetic waves. When this energy, which is from the sun is absorbed by your hand, the molecules in your hand begin to move much more quickly, and we know that the average temperature is defined as the average speed of the molecules. So as the speed of the molecules begin to increase, the temperature in your hand increases. And so that energy from the sun is released into your hand. So your hand absorbs energy from the sun. Now, there are several different things in this particular graphic. The type of radiation, we can describe radiation in terms of radio waves, television waves, microwaves, infrared, which means near red, visible light, which we're all familiar with, ultraviolet waves. If you're out in the sun, you're exposed to UV radiation. If you're not careful, that can lead to skin damage, and in severe cases, skin cancer. And then X-rays. Now, one of the things, these are the different types of radiation. What do you notice about the wavelength of each of these types of radiation? And by the way, the wavelength is defined as the length from the crest of a wave to the next crest. So this is a ridge, and this is a trough. Ridge, trough. So we would define this as one wavelength, lambda. That's the Greek alphabet. That's how we'll describe wavelength in terms of lambda. Now, the typical wavelengths, which are measured in meters, we see that radio waves have 100 meters between each crest of the ridge. Whereas we go down to X-rays, and it's a very small, 10 to the minus 9 meters. It's a very small. In other words, going from here to here, you see the little ridges and troughs. Very small wavelengths. Visible light is about 5 times 10 to the minus 7. In other words, if we were to look, if we were the wavelength of visible light going from this ridge to this ridge here, the crest of that ridge is 0.000. It's very small. One too many zeros. So very small wavelength. Now we will do a conversion from meters to microns. So it'll give us a standard way of measuring this. Well, let's look at the relationship between radiation and temperature. There's actually a formula that relates the amount of radiation emitted by an object. That's what this E is. The maximum rate of radiation emitted by a square, or by the square meter of a surface of an object. It's related to temperature raised to the 4th power. You'll also notice there's a sigma value, sigma written like this. It's a Stefan-Boltzmann constant. It's a number. But really, when you're talking about the amount of energy that's emitted by an object, whether it's your hand, it's a table, it's a needle, it's water, it's the sun, it's the surface of the ground, anything that radiates will have a temperature associated with it. So if we increase the temperature, the energy emitted also increases. And in fact, temperature the 4th power. A small increase in temperature will result in an increase in the amount of radiation emitted by an object. Now, this temperature is measured in units of Kelvin. Now, the sun's surface temperature is about 6,000 Kelvin on average. If you look at the Earth's temperature, it's about 288 Kelvin on average. So the temperature of the sun is a lot less than the temperature of the the temperature of the Earth is a lot less than the temperature of the Sun. And if we say the amount of energy emitted is related to sigma t to the fourth power, which one of these objects are going to emit more energy? The Sun or the Earth? Well, if I plug in 600 or 6,000, which is the temperature of the Sun in Kelvin, raised to the fourth power compared to the temperature of the Sun in Kelvin raised to the fourth power, obviously this number is going to be a lot larger than this number. So the Sun puts out more energy per square meter. That makes sense. The Sun is very energetic. So we can say that the Sun emits much more energy than the Earth. But the Earth also emits energy, right? And in fact, anything that has a temperature emits energy because of this equation called the Stefan-Boltzmann equation. Energy of an object, the amount of energy emitted, is related to some constant times temperature raised to the fourth power. Now, there's another way that we can look at this radiation, and there's a lot of things going on in this graph, so I'm going to take a little time to explain what we're looking at here. In the y-axis is the intensity of radiation, measured in watts per meter squared per micron, which is how we measure the wavelength of energy. The micron is actually much smaller than the diameter of your hair, quite a bit smaller. So that gives you an idea of what 1 micron is equal to. So we look at the intensity, and we go from 0 to 2 times 10 to the 7, 4 times 10 to the 7, 6 times 10. So you see the energy emitted, the intensity of radiation, increases as we go from 0 up to 8 times 10 to the 7. And the units are in watts per meter squared per micron. The length of these waves, remember we talked about wavelength. Let me just jump back here a second. Remember we talked about wavelength, the length between the crest of these waves. And recall that with visible light, very small. And so notice that the Sun, and this is the total amount, everything under this curve, I should point out. If you were to measure the total amount of energy under this curve, that is the energy put out by the Sun. And notice that the Sun emits energy at all wavelengths. But what we're looking at in this particular example is the wavelength going from 0.4 to 0.7 microns. Very small wavelengths. That actually corresponds to visible light. Our eyes can actually see radiation that measures anywhere from 0.4 to 0.7 microns. That's the way of our physiology. And so what we notice here is that the Sun emits most of its peak energy, this 8 times 10 to the 7, at about 0.5 or 0.55 microns. So the most intense radiation occurs in the visible portion of the electromagnetic spectrum. Now, if we look at the Earth, which radiates at 288 Kelvin, or it has a temperature of 288 Kelvin, we look at the total energy that the Earth emits, which is all of this area underneath this curve, and notice the radiation intensity, again in watts per meter squared per micron, but very small compared to these values over here. And so at about 8 watts per meter squared per micron, 16 and 0. Notice that the Sun emits most of its energy at what wavelength? The intensity is about 17, 18, but it emits most of it at 10 microns. So the sun's wavelength of maximum emission, where it emits most of its energy, is at 0.55, or we can just say 0.5 micrometers, compared to 10 micrometers. So what does this tell us? Well, it tells us that the Earth emits its energy at longer wavelengths. 10 is larger than 0.5. And so when we're talking about the radiation that the Earth emits, we refer to that as long-wave radiation. So anytime you hear me talking about long-wave radiation, I'm talking about radiation that's emitted anywhere from 5 to 20 microns. And I'm talking about everything on the Earth. If we talk about short-wave radiation, that's the radiation emitted by the sun. Now there's a relationship where we can actually calculate the peak of maximum emission of energy of the sun and of the Earth. In fact, we call that Wien's law. So there are three equations that we've looked at in this particular chapter. The first one had to do with temperature conversions, going from Celsius to Fahrenheit, Fahrenheit to Celsius, Celsius to Kelvin. So that's one set of equations. We talked about the Stefan-Boltzmann equation, where we can calculate the amount of energy being emitted by an object. It's actually relative to the fourth power of the temperature of an object in Kelvin. And then Wien's law, which tells us the wavelength of maximum emission. And there's a constant here. It's about 3,000. And the temperature in Kelvin of an object. So let's do some calculations. Let's see. Let's say we wanted to find the wavelength of maximum emission for the sun. If we take 3,000, which is what this constant is, and divide by the temperature of the sun, what did we say the temperature of the sun? About 6,000 Kelvin. So we take 3,000 and divide by 6,000, and we come up with 0.5 microns. Interesting. That's what we find here. The peak of the largest amount of energy occurs at 0.5 microns. That's in the visible spectrum of the electromagnetic radiation. Well, we know that the sun, according to this, or the Earth, according to this particular graph, the maximum peak of emission should be at about 10 microns. Well, let's try that. Let me erase some of this. So again, we're looking for the Earth, the maximum peak of radiation. Again, we use 3,000 as the constant. The Earth, we said, was 288 Kelvin, but to make this calculation a bit more simplistic, let's use 300 Kelvin, and we come up with 10 microns. So that gives you an idea of how to calculate the peak of energy emission based upon the radiative temperature of an object. Now, the previous slide we looked at the wavelengths from 0.4 to 0.7. But if we look at this curve, which is the energy of the sun emits energy all the way out to the AM radio waves. In other words, the sun emits energy with wavelengths on the order of 100 meters here, AM radio waves. So the sun emits energy at short wavelengths. In fact, most of its energy is emitted from about 0.2 to about 1.5. These are what we call shortwave radiation. But it also absorbs less energy all the way out to 100 meters in terms of wavelengths. Keep in mind, our eyes are receptive to the wavelengths from 0.4 to 0.7. Now, once we go out Well, I'll get back to that in a second. I was getting ready to talk about long-wave radiation, but I'll hit that here in just a moment. So basically what we're getting from this particular slide, again, this is all the energy emitted by the sun, is about 88% or almost 90% of the amount of radiation that the sun releases occurs at wavelengths less than 1.5 microns. So what we're saying here is that the sun emits almost all of its energy, about 90% of its energy, from wavelengths from about 0.2 to 1.5 microns. So we call the radiation emitted by the sun shortwave radiation. Now with the Earth, notice that it emits most of its energy between 4 microns and 20 microns. So any wavelength greater than 4 microns, we term this as long wave radiation. In other words, we call it, you might also hear me refer to it as infrared, which means near red. Again, if we look at the spectrum here, this is the red. You've heard of Roy G. Biv in terms of the colors. Well, here's your red, and wavelengths that go out beyond that is near red, which we call infrared. I'll use the long wave infrared interchangeably. So, we hear about all this stuff with radiation. How can we use it in terms of weather? Well, clouds have a temperature, and by the Stefan-Boltzmann law, we know that it emits at the fourth power of temperature, so it emits radiation. And in fact, we can look at clouds at night, and what you see here is a map of the U.S., and you can see the clouds. Actually, what you're seeing is the radiation emitted by the clouds in this infrared imagery. Now, as you're aware of, anything that has a temperature, any object that has a temperature, will emit radiation. We saw that from the Stefan-Boltzmann law. And believe it or not, clouds, which are objects, emit radiation too. Clouds have a temperature. And in fact, what's nice about this, and we'll get into imagery, satellite imagery later, but at night, when we no longer have the sun as a source of light to see clouds from the satellites that orbit the Earth's surface, the clouds themselves actually emit energy. And in fact, you remember the Stefan-Boltzmann law, the amount of energy emitted by an object, in this particular case clouds, is related to that constant, sigma, and the fourth power of temperature. And so what the satellites do is that they measure the temperature of the clouds. And based upon that, they can see how much energy the clouds emit. And so that is one reason why we can see clouds at night. Notice if you're watching the 10 o'clock weather, they will be using, for their satellite imagery, they'll use infrared at night because clouds emit energy. They have a temperature, and so this allows us to visualize clouds. Water vapor is another type of imagery. Water has a temperature, specifically water vapor, and so it emits energy. So when clouds emit their maximum energy at a certain wavelength, we can actually measure these with sensors, specifically infrared sensors housed on these satellites. So you're beginning to see why understanding radiation is important. It's a way of transferring energy in the atmosphere, which we'll learn later will form clouds, thunderstorms, severe thunderstorms, tornadoes. But it also allows us to see objects, such as clouds. Now, there's a balancing act of radiation. There's absorption of radiation, emission of radiation, and equilibrium of radiation when things are in balance. Let me ask you a couple of questions here. If the Earth and all things on the Earth are continually radiating energy away, this is the key, radiating energy away, why don't we get progressively colder? Well, it's probably because the Earth is actually absorbing some energy. Yes, the Earth emits energy in the long wave spectrum, or in the long wave range of the electromagnetic spectrum, but it also absorbs energy. It absorbs energy from where? Well, your first guess is probably the sun. So the Earth absorbs energy from the sun. Objects on the Earth absorb energy. For instance, in the classroom, in this spring 2008 offering, we have, I believe, 24 students in this classroom. If we were to double or triple the number of students in this classroom and keep the same classroom, you would notice the temperature becoming very uncomfortable in the classroom. And it's because each of you are emitting energy and absorbing energy. Well, let's look at it like this. Let's say we have object A, which emits energy. And in fact, it emits more energy than it absorbs. What do you think will happen to the temperature of object A? Will it warm? Will it cool? Will it stay the same? What if object A emits less energy than it absorbs? What if what the object emits is equal to what it absorbs? Well, if object A emits more than it absorbs, it will begin to cool. It's losing energy. It's emitting more than it's absorbing. If the amount that the object, and this could be any object, your hand, let's say your hand emits less energy than it absorbs, then it will begin to warm. It's all part of a balancing act. Now if your hand emits, the amount that it emits is equal to the amount it absorbs, then it stays the same. So the key to all this is we need to figure out the energy budget of the Earth and the atmosphere. Now, absorption and emission depends upon several things. How well an object absorbs radiation or emits radiation depends upon the color of an object, the texture of the object, whether it's rough or smooth, the moisture present in the object, and the actual temperature of the object. So for instance, I give an example here of a black leather interior of a car or the asphalt road. They typically heat up rapidly during the day. Darker colors tend to absorb energy much more efficiently than lighter color objects. The moisture characteristics of an object. We talked about that also. We noticed in the soil, between the dry and the moist soil, dry soil can absorb energy and process that much more quickly. Now, if it absorbs it, what will it do with the energy? We talked about energy partitioning earlier, a little bit earlier in this. The temperature of an object. We know that as the temperature of an object increases, the ability for it to emit becomes larger. So the absorption and emission characteristics depend upon these things, and we'll come back to these in just a few minutes. Now, before we go any further, there's another definition. Boy, there are a lot of definitions in this chapter, but these definitions are setting the stage for the rest of this course. We have something called a black body. And a black body is basically defined as an object that is a perfect absorber. In other words, it absorbs all the radiation that it receives, and a perfect emitter. It emits everything that it receives at a particular temperature. There are two black bodies that we'll be talking about. The Earth is a black body, and the Sun is a black body. Now, since the Sun and Earth are both black bodies, we can use the Stefan-Boltzmann and Wien's law on them. Now let's define something called radiative equilibrium temperature. Now radiative obviously has something to do with radiation. Equilibrium means in balance in temperature. So we're looking at a balance in temperature based upon radiation. So if we look at this in terms of the amount that the Earth absorbs shortwave radiation from the Sun, if that is equal to what the Earth emits in terms of long-wave radiation, remember the Earth absorbs short-wave radiation from the Sun and it emits long-wave radiation, then our average temperature should be 255 Kelvin or 0 degrees Fahrenheit. So what this is saying is that based upon if we have a balance between what the Earth absorbs from the Sun and what the Earth emits, because the Earth has a temperature and so it emits radiation, then the average temperature at the Earth's surface should be 0 degrees Fahrenheit. Well, we know that's not true. And in fact, our average temperature is right around 59 degrees Fahrenheit. So what's going on here? Now, we've talked about the Earth and the Sun being black bodies. However, the problem, or I don't know if it's a problem, I shouldn't call it a problem, but the complicating factor here has something to do with our atmosphere. And in fact, our atmosphere is not a black body. In fact, it is a selective absorber and a selective emitter. It's not a perfect absorber and emitter. At some wavelengths, the atmosphere will not absorb radiation. At other wavelengths, it will. At some, it will not emit, and others, it will emit. So the atmosphere throws in a complication. Here's a good example. Think about your car windshield. In terms of shortwave radiation, UV rays, the type of radiation that produces damage to your skin, and infrared radiation, long-wave radiation, are absorbed by the windshield. Okay, so very short wavelengths, such as UV rays, which are on average between 0.2 and 0.3 microns, and long-wave radiation, anything greater than 4 microns, are absorbed by the windshield, but visible light is passed through the glass. So from 0.4 to 0.7 microns, which is the wavelength of visible light, it passes through the glass. So that your car windshield is a selected absorber. In other words, it will not absorb the radiation between 0.4 and 0.7. That's why if you're sitting out in a parking lot reading a book during the day, you can see, because that visible light passes through the car windshield. It's the same thing with our atmosphere. The atmosphere is a selective absorber and emitter. So we need to learn a little something about the radiative characteristics of the atmosphere. But before we do that, yet another definition. It's called Kirchhoff's law. It says that good absorbers are also good emitters at a certain wavelength. Remember, we're talking about selective here. So, and also poor absorbers of energy are also poor emitters at a particular wavelength. For example, this picture here. Can you tell me why you have this type of hollowed out circle around trees? Right here and here. And in fact, if you're listening to this video now and you've got some trees and there's snow on the ground, go take a peek. Pause the video for a moment and go take a look and see if you can see these depressions. Why is this occurring? Well, We know that trees absorb shortwave radiation from the sun. The trees are absorbing energy, but they're also emitting energy. And in fact, trees emit long-wave energy, and it's absorbed by the snow. And so, the snow begins to evaporate. And so the tree, so snow in this particular case, can absorb long-wave radiation. And so that is why you have these hollowed-out depressions. So if snow is a pretty good absorber of infrared radiation, it's a pretty decent emitter also. And so if snow is rapidly emitting long-wave energy, what's the temperature near the surface? It's probably pretty cool. Now, if we're looking at the atmosphere, what we're going to do at this point, and this is a figure in your textbook, I believe it's in your textbook in Chapter 2. If not, you'll have it here. But it's the percent absorption by atmosphere and its gases. So you know the atmosphere has nitrogen running around about 79% based upon concentration, 20% oxygen, trace gases less than 1%. And of course, water vapor varies. It is a variable gas, anywhere from 0 to 4%. And so what we have here, there's a lot of information going on here. I'm going to break this down slide by slide. But we're going to take a look at the absorption, or the percentage absorption of energy that's done by nitrous oxide, methane, molecular oxygen and ozone, water vapor, carbon dioxide, and then this bottom graph will look at the total atmosphere. Now again, there's a lot going on here, and so what I've done is I've broken this down. And what we're looking at in the y-axis is the amount of absorption of radiation. So it goes from 0%, 50%, 100%. We could make this 25% here. 75. I know this is getting messy. Let me go ahead and clean this up. So again, this is percentage of absorption of energy of nitrous oxide. So nitrous oxide is running around in the atmosphere, and it absorbs radiation at about 4 microns, almost 100% of all long-wave radiation. Again, anything longer, 4 or longer, we consider long-wave energy, long-wave radiation. So nitrous oxide in the atmosphere will absorb almost 100% of energy at 4 microns. Also, at about 8 here, it absorbs almost 90% of radiation, long-wave radiation. What about visible light, which is about 0.4 to 0.7 here? This is visible light. How much visible light, or how much radiation, 0.4 to 0.7, will nitrous oxide absorb? Now that visible light is coming from the sun. We're in the short wavelength here. VL here is visible light. So we have energy coming down from the sun in the visible spectrum, 0.4 to 0.7. How much is nitrous oxide absorbing? 0. It's not absorbing anything. In fact, it's not absorbing anything less than about 1.5 microns. And anything longer than about 9 microns, or about 9.5 microns, it's not absorbing. Well, we really don't care so much about nitrous oxide, at least in terms of absorption characteristics. Now, when we talk about greenhouse gases, we'll come back to this later. Methane, the stuff that cows put out with their digestive system and their belching. We notice that at about 7 microns of radiation. There's almost 90% absorbed. So methane does a very good job of absorbing long-wave radiation of 7 microns. Same thing down here with 2 microns. But everywhere else, it absorbs 0% of radiation. So this first slide, not a whole lot going on. Now, with this one, however, if we look at the wavelength, again, going from 0 to 0. Looks like about 0.3 here, oxygen, molecular oxygen, O2, and ozone, O3, absorb almost 100% of incoming ultraviolet radiation. Ultraviolet radiation, the UV rays that we're all concerned about, is about 0.1 to 0.3. Ozone and oxygen do a very good job of absorbing that particular wavelength of ultraviolet rays. But now if you go to the 0.4, or just slightly past 0.3, you still have some UV getting through to the surface because the amount absorbed is about 5%. So you see why it is important for ozone to be present in the atmosphere. Because if it's not, then those UV rays make it to the surface and they damage our skin. So you hear about the ozone hole down over the over Antarctica, and you hear about thinning ozone in portions of the northern hemisphere. And without as much ozone present, it can let more of the ultraviolet radiation through, which can lead to skin damage and, in many cases, skin cancer. Now, you'll notice that the other wavelengths, in the visible region 0.4 to 0.7, there's only about 10% of visible light that is absorbed by molecular oxygen and ozone. At around 9, there's almost 100%, so at 9 microns, molecular oxygen and ozone can absorb long-wave radiation, and objects on Earth emit long-wave radiation. Let's look at water vapor, and water vapor is really a major player in terms of warming and cooling our atmosphere. You'll notice that with the presence of water vapor does not absorb any wavelengths less than about 0.8. If you look from 0.8 all the way back, in other words, all the visible light from 0.4 to 0.7, water vapor will not absorb. So the sun emits in the wavelength of 0.4 to 0.7. So if there's water vapor present outside, the sun cannot absorb that. Ultraviolet radiation, 0.1 to 0.3, the sun does not, or the water vapor does not absorb. However, notice strong absorption bands that occur from 1 to 4 and from about 4.5 to about 7. Water vapor will absorb almost 100% of radiation that's emitted in this particular wavelength. And even further out, when you go to 12 to about 18, about 50% of long-wave radiation is absorbed by water vapor. So why do we care if water vapor absorbs long-wave radiation? Well, recall earlier from the chapter that any time an object, and this can be a water vapor molecule, absorbs energy, whether it be long wave or shorter wavelengths, every time it absorbs energy, the temperature of that water vapor or other molecule begins to increase. And so, if the temperature of that water vapor molecule begins to increase, we know from Stefan Boltzmann's law that the amount of energy it releases or emits increases also. We'll tie this together here in a few moments. You hear about carbon dioxide. Now, almost everything below 1 micron, carbon dioxide does not absorb, but you have some strong absorption bands at about 2 and about 4 microns. So CO2 does absorb some shortwave radiation in very narrow bands. However, CO2 really begins to absorb very strongly at wavelengths greater than about 13. So any object on Earth that emits energy at greater than 13 microns, CO2 will also absorb that. In other words, it cannot pass out into the atmosphere. So the question is, what happens when these gases, such as water vapor and CO2, absorb long wave, in other words, infrared radiation from the Earth? Well, the molecules gain kinetic energy. And we've learned that as the kinetic energy increases, the number of collisions increase, which increases the kinetic energy, which leads to an increase in temperature. So the question now comes, what happens when these gases, such as water vapor and CO2, absorb long-wave radiation from the Earth? To understand this, we're going to look at two different scenarios here. In this first one here on the left, what you see is the sun emitting shortwave energy to the Earth and no atmosphere. We're assuming an Earth with no atmosphere. So what the sun emits and what the Earth radiates away in terms of long-wave energy that we see here, our average temperature would be about 0 degrees Fahrenheit. Now keep in mind, the sun is it's a black body, a perfect emitter, perfect absorber. The Earth is also a black body, a perfect absorber and perfect emitter. So what the Earth receives, it emits out. And so what we have here is the reason for this 0 degree Fahrenheit is because of a lack of atmosphere. Now if we look at the right hand portion of this picture, now you see an atmosphere. From the surface on up, all of this is an atmosphere. And that atmosphere is composed of water vapor, nitrogen, oxygen, ozone, other trace gases. Now, let me go ahead and erase this just for a moment, clear this off. Now, what happens is that the sun emits shortwave radiation, and very little of it, depending upon what's present, it reaches the surface of the Earth, and what will happen as the Earth receives the energy, it will begin to emit long-wave energy out to outer space. But some of it, as it's going out, is absorbed by the atmosphere, such as water vapor, CO2, and other types of gases. So as the atmosphere absorbs some of that long-wave radiation leaving the Earth, its temperature increases, and by the Stefan-Boltzmann law, its temperature increases, so does the amount of energy that it emits. And so now the atmosphere begins to emit energy back toward the surface of the Earth. So now you will have some energy. Again, the energy of the Earth, the temperature will increase, and it will begin to emit energy. Some of that energy will go out into space. However, some of it will be absorbed. And then the atmosphere will begin to send energy back down to the surface of the Earth. And so it's because of this atmospheric effect, which is defined as the gases in the atmosphere, as they absorb some wavelengths of radiation, they will also emit those wavelengths of radiation and emit some of those back toward the surface of the Earth. Because of the presence of that atmosphere, that is why our average temperature globally is 59 degrees Fahrenheit. So it's this absorption of not only shortwave radiation, but long-wave radiation is the big player here. So now, if what the Earth absorbs from the Sun is equal to what it emits, its average temperature would be 0. Remember that? I said, what's up here? But because of this atmospheric effect, our temperature is 59 degrees Fahrenheit. So it's actually very fortunate that we do have an atmosphere, not only for breathing, but also for keeping our temperature warmer than if we had no atmosphere. And so now let's go and look at this absorption pattern for the total atmosphere. And that's adding in all of the other gases, such as CO2, oxygen, ozone, methane, nitrous oxide, all the gases that we looked at before. You'll notice that from about 0 to 0.25, there is almost 100% absorption of shortwave radiation, and shortwave radiation coming in from the Sun. And it's because of ozone. So it's fortunate that we have that. And then we go from about 0.3 to 0.7, which is the visible spectrum. Again, we're talking shortwave radiation. The Sun is the source for shortwave radiation. And so most of that energy that's between 0.3 and 0.7 microns makes it all the way to the surface. Now we get over here and notice that at about 4 to 7 we have a large band of absorption, and also from about 11 on we have a large band of absorption. And remember, anything that's 4 microns or greater we're going to consider long-wave radiation, or the source being objects from the Earth. Now notice that there's something called an atmospheric window, where only about 25% of long-wave radiation, 25%, is actually being absorbed by gases in the atmosphere. So it would be very interesting that most of the energy in these two particular wavelengths, at about 7 and about, it looks like about 10, should send all that energy back out to space. But that doesn't happen. And in fact, as we'll see here, clouds tend to close that atmospheric window. So this is really your first forecasting lesson here. When clouds are present, incoming shortwave radiation from the Sun cannot penetrate the clouds and is reflected out. That's why when you have cloudy days, it's dark outside, or darker. Now, what you see here is what I represent as the surface. Anytime I draw a line like this with diagonals, that's the Earth's surface. So the Earth's surface emits long-wave radiation. That energy is absorbed by the clouds. It's not reflected, it's absorbed. Some of it's reflected, but the majority of it's absorbed. So the temperature of the cloud, or the gases that make up the cloud, begins to increase. And by the Stefan-Boltzmann law, as it increases, as the temperature increases, the amount of energy emitted by the cloud back down to the Earth also increases. So now the cloud is emitting infrared or long-wave energy back to the surface of the Earth. So during the day, temperatures would stay cooler than normal because the shortwave radiation is reflected away. At night, however, the source for energy are clouds, at least in terms of radiating energy back to the surface. That's the reason why cloudy nights, temperatures do not drop so dramatically. There's our energy source at night. So again, just to summarize, daytime clouds keep temperatures down. It reflects some of the Sun's incoming shortwave radiation. The cloud itself will emit long-wave radiation to the Earth's surface. At nighttime, outgoing long-wave radiation, in other words, radiation coming from the Earth, is absorbed by the clouds. Cloud's temperature increases, and it emits energy back to the Earth's surface. So we see that the atmospheric effect, such as water vapor, even CO2, carbon dioxide, in moderate levels, play a positive role in our temperature unless we have an enhancement of the atmospheric effect. And in fact, we've seen over the 20th century globally about a 1 degree Fahrenheit increase. And in fact, current climate models predict that if we continue to pump in CO2, carbon dioxide, into the atmosphere in levels that are higher than what we've seen in the past, we can expect about a 3 to 10 degree temperature increase over the next 90 years. So the last 100 years we only saw 1 degree increase. Now they're projecting 3 to 10 degrees Fahrenheit. So what's going on here? Well, if we increase CO2, methane, nitrous oxide, chlorofluorocarbons, CFCs, then the long-wave radiation that's emitted from the Earth, again, long-wave radiation greater than 4 microns, will be absorbed by these atmospheric gases and will be unable to escape to space. And so CO2 and methane and nitrous oxide will radiate that energy back to the Earth's surface, increasing temperatures. And in fact, now this is something you won't have on the test, this stuff with CFC, but it's kind of interesting. CFCs, which are refrigerants, chemicals used in refrigerants, can actually absorb 8 to 11 micron wavelength, in other words, the atmospheric window. And in fact, one CFC-12 molecule, one of these, is equivalent to 10,000 molecules of CO2. Now, lately we've gotten better control of our CFC over the last decade, and so hopefully that will not play a role in enhancing our atmospheric effect. Just a few more bits of information that you should be aware of. Water vapor accounts for about 60% of the atmospheric effect. So H2O, water vapor, is a big player. CO2 plays a significant role, about 26%. And other remaining greenhouse gases, such as methane, nitrous oxide, and a couple of other gases, play a role. So let me ask you this. What happens to water vapor content, in other words, water in the gaseous form, if we increase surface temperatures? Look at this background on this PowerPoint slide. It's a background of water that we see here. What if we were to increase the amount, what if we were to increase temperatures? What would happen to the evaporation of water? Well, it would increase. So we would increase water vapor. If we increase water vapor, and we know that water vapor is a very big absorber of long-wave radiation, how would this affect our temperatures? Well, it should increase our temperatures, since water vapor is a strong greenhouse gas. Now, think about it like this, though. So let's say we increase the amount of water vapor in the air, which could increase the amount of clouds in the air. Well, we said earlier that clouds tend to reduce the amount of incoming short-wave radiation, radiation coming in from the sun. So it's kind of interesting, if we increase the amount of CO2 in our atmosphere, our daytime temperatures may not be as high as they used to be, but our nighttime temperatures would begin to increase because of the presence of clouds. Remember, long-wave radiation is absorbed by the clouds, and the long-wave radiation comes from the surface, Earth's surface. And then the temperature of the clouds increase, and it radiates energy back to the surface, keeping nighttime temperatures warmer.